Welcome to the third lecture of software quality assurance. In the last lecture we talked about software defects in quite a bit of detail, and we also talked about different defect elimination strategies. And in particular we looked at defect removal techniques, and primarily we looked at two techniques, inspections and testing. Although we will talk about inspections and testing in much more detail later in this course, but we looked at how inspections are used for defect removal and how testing is used for defect removal. Inspections are basically direct fault finding activity or direct defect finding activity and then elimination. On the other hand, testing is observation of failure and then removal of the causes of the failure. Today we will continue our discussion on software defects. However, the good part of the lecture today would be covered by defect prevention. There are a few things that I would like to talk about before we discuss defect prevention. One of the things that needs to be understood before we delve in more detail on defects and defect prevention, defect elimination, is the concept of defect repair rates. Now, what is defect repair rate? Defect repair rate is how quickly defects are fixed after they have been identified, after they have been discovered or detected. It is very unfortunate that the reported data on defect repair rates is not consistent. It is not clear as to what really the defect repair rates are. Remember, we talked about in the first lecture the efficiency of fixing defects when they appear, and this we took as an aspect of software quality. And so we cannot ignore this very important topic, a very important corollary of software quality assurance. Now, it is interesting that, and very obvious I would say, that defect repair rates usually decline as cyclomatic and essential complexity increases. Now, these are two different measures of complexities of software products. One is cyclomatic, the other is essential. And these complexities, if they are present in the software, that is, higher the complexity, lower are the defect rates. And that's a very obvious observation, that if the software is complex, it is difficult, it takes longer to repair the defects, even if they have been discovered. And these things really come into play when a failure has been observed. That is, some sort of testing has been performed, and as a result, a failure has been observed, and there is an effort to eliminate the causes of the failure. Now, if the software is complex, to actually reconstruct that problem and to find where the problem lies is a difficult thing to do. And if the complexity of the software and the complexity of the domain are an added problem, then obviously it is going to take more time to fix those defects and to remove the causes of failure. On the other hand, defect repair rates usually improve or go up or increase as the experience with the application domain, with experience of the language that we are using, and if we are performing inspections, the defect repair rates improve if we follow certain structured methodologies for the design and development of the software. And so we conclude that the software engineering community, which had developed these methods and techniques for the improvement in development and in the development of software products, has rightfully claimed that the use of these methodologies, the use of these techniques and processes improve the quality of software, because we have seen that the defect repair rates increase with the use of these methodologies and techniques. It is also very interesting to note that defect repair rates are higher for maintenance specialists as compared to other professionals in the software engineering community. It is because the maintenance specialists are very focused. They are trained to find and repair defects, and so it is very obvious that their performance would be better than, let's say, a person whose primary task is to do programming. For coding errors, comments are useful, and a study performed by IBM concluded that 18% of comment density is ideal. If you have fewer comments, or if you have more than that, then comments may not help in improving the defect repair rates. And it is also found that flowcharts had no help in improving the defect repair rates. However, good error messages were of very good help. This again relates back to the thing that I talked about a little bit earlier, and that is that these things are pointed out by the execution of software tests. Software tests indicate that a failure has occurred, and we have to go and find the cause of the failure and eliminate that cause so that the defect goes away. But what we also have to do is to ensure that we do not introduce new defects while we are conducting what is known as introducing bad fixes, that we go and instead of removing defects, we add new defects in the maintenance activity. And so if you remember our discussion on the origins of software defects, errors in bad fixes was also a very important origin point at that time, and it continues to be continues to be an area of worry for project managers. And so regression testing has to be performed so that to ensure that original functionality is still there and it's not been compromised. There is another concept which is interesting, and it is considered unpleasant by many in our community, and that is defect seeding. Defect seeding is willfully inserting errors in software prior to an inspection or a review or a testing activity. Now, why would one do that? We would want to introduce errors into software willfully because we would want to accurately test the removal process. Now, if we introduce errors into software, we know we have errors in the software, and then we give them to human inspectors for reviews or inspections, and then they are able to find those errors, then we would know that our removal process is working. Or if we can put them through a testing activity, and at the end of the testing activity we have accurately found all of them, then we can be happy that yes, our software testing activity has been successful in finding all these defects. This, and that is the defect seeding, can provide us with an insight of what the defect removal efficiency will be of this particular software product. And if our defect removal efficiency is low, then we can improve it by applying different other techniques for software quality assurance. And so, although it is not practiced by a large number of companies, but this is still a good idea to check the accuracy of our testing activity, to check the accuracy of our inspection and review process. There is another thing that we talked about in the last lecture, and that was the impact of defects on the real world, if the application fails. Now, every defect does not have the same severity level. Some are just cosmetic, while others are have a very lasting negative impact. So we can have 4 levels of defects, or we can say that 4 severity levels of defects. Severity level 1 are those defects which cause an application to fail totally. The second level, those defects would be marked as failure of major functions. Third severity level are minor problems, and fourth are cosmetic problems, problems which do not in any way hinder the functionality of the software application. However, there may be some typographical errors, there may be some odd combination of colors, there may be some colors which are not liked by the customer, or placement of some input fields or output results in positions which are not preferred by the customer. These are cosmetic problems and should be eliminated from the application, time permitting, and upon the insistence of the customer. But obviously those defects which cause applications to fail or which cause major functions to fail should get the top priority in terms of number one, detecting, and number two, fixing those defects. We also talked about a little bit on defect tracking. Why is it important to track defects from the perspective of from where did they come into the application, when they were discovered, who discovered them, what was the cause of the mode of discovery, was it testing, was it inspection, was it reviews, and how it was fixed. So defect tracking is a very important topic when we are dealing with software quality assurance. And defects are tracked for severity levels. They are tracked from who is going to fix them, that is, where are they routed, which personnel are responsible for finding a solution to the problems identified by a defect discovery, and there needs to be a record of multiple reporting of defects or duplicate defects in an application. There may be some reports which are thought as of defects, but in fact they're not defects, and a customer may not be fully aware, or a user may not be fully aware of the functionality. And we see that all the time, that sometimes a report comes that this is a defect, while in fact it's not a defect. And for every defect, we need to keep the repair information, how quickly it was repaired and provided to the customer, and was the defect severity level forced us to release a patch immediately, or it was just a cosmetic defect which can be corrected in the next version. And so defects must be tracked, and when they are tracked, then and only then we can observe their defect repair rates, whether they are improving or whether they are not improving or decrease, or the defect repair rates are going down. Now, for the rest of the lecture, we will talk about defect prevention. What we really want is the defects to not enter our work products. We do not want errors, mistakes, faults in our requirements. We don't want them in our design. We don't want them in our code and other documents. So we don't want to have to deal with defects. Now that's the ideal situation. We do not want defects in our work products. They are not welcome. So to do that, we have to prevent them from getting into our work products. Defect prevention is a difficult concept. It is a difficult concept to understand. It is a difficult concept to study and to quantify that yes, our products are good because we have prevented defects from coming into the work products. Take an example of the medical science. Prevention is better than cure, right? That's just the philosophy in software also. So defect prevention is better than defect removal. But we cannot quantify it absolutely, that our products are better because we have applied different prevention mechanisms. What we can what we have to do is to try to measure these as accurately as possible. How can we apply defect prevention, or what are the issues in defect prevention we are going to study today? Let's look at the philosophy of defect prevention. If human misconceptions are the error sources, then education and training can help us remove these error sources. We have to understand why an error occurs. So if an error is occurring because of the misconceptions of humans, of IT people, then we can provide them education and training so that we eliminate that source of error. If imprecise designs and implementations that deviate from product specifications or design intentions are the causes of faults or failures, then formal methods can help us prevent such deviations. The first is, if misconceptions of humans are the source of error, then we can have education and training. On the other hand, if imprecise design and implementations are the causes, then we can have formal methods and structured approaches to eliminate those sources of errors. If non-conformance to selected processes and standards is the problem, then process conformance and standard enforcement can help us in the prevention of those errors, or prevention of those, elimination of the sources of errors. If certain tools or technologies can reduce fault injections or can reduce errors, the number of errors coming into our software products under similar environments, then they should be adopted. And so for every fault, we have to try to find the source from where it is coming, and then find the cause why it's coming into our work products, and then we try to eliminate the cause. And if we try to eliminate the cause and we are successful, then we have eliminated the entry of faults into our work products. And that's what defect prevention is. Now let's talk about education and training. Education and training is one of the most fundamental ways of improving our work products. It's a twofold thing. We can improve the product, and we can also improve the person who's developing the product. This course is part of that education and training that you are taking. It provides, it helps the people-based errors to be eliminated from software products. And I'm not talking about removal, I'm talking about elimination, which consists of both prevention as well as removal. The people factor is the most important factor that determines the quality and ultimately the success and failure of most of software projects. And so by providing education and training to the people working on software projects, we are improving the quality of the software directly. It's not an even indirect relationship, it's a direct relationship. When people learn to do things better, they apply their knowledge, they apply their newly acquired skills to do the right thing, to develop software which consists of high quality, or which is of high quality. So, education and training is very important in improving the source, in improving the quality of software, and for all those errors which come through humans, if we get them good enough education and good enough training, then we can prevent those sorts of errors from coming into the work products. With their education and with their training, the humans, that is the IT professionals, control, manage, and improve the way they work. And if we can control, if they can control and manage and improve their professional activity, their professional tasks, what else is needed? That's what quality is all about. People are working on projects, people are working on products. Software engineering is a human intensive activity. And if people who are performing this activity are trained well, are educated well, they can do their jobs wonderfully. The focus of education and training should be on 4 things. Number 1, product and domain specific knowledge. This is very important. Paramount importance should be given to this, that people who are working on accounting projects should have basic knowledge of how accounting works. If they're working on hospital information systems, they should know how hospitals are run. If they're working on nuclear energy, nuclear science, they should have good enough knowledge of nuclear science or nuclear engineering. If they're working on locomotive design, then that's what they should learn. So product and domain specific knowledge should be part of education training. Number 1, most important. Secondly, software development knowledge and expertise. If you are trained in Java and your current assignments require that you work in C++, you should get some help. If you are a self-learner, go get a book or go to the web and learn C++. But if you are one of those who requires some basic hands-on teaching type training, go join a class, get some training. But you need to be familiar with the tools, you need to be familiar with the development knowledge and expertise. And that is again very important. Third, you should know about the development methodology, technology, and tools. Increasingly, companies are using, let's say, rapid development approaches, or increasingly, some companies are using XP type software processes, agile software processes. And so, if you're working in that environment, you need to know the agile manifesto. You need to be comfortable with very rapid development and to be able to take all challenges in a daily task, be a designer, be a developer, be an integrator, all in one day. And you also have, lastly, the development process knowledge, the processes that are being applied, the SQA processes, the configuration management processes, the development processes, the testing processes. And so these are the 4 areas where education and training should be focused. The second area that we talked about was the focus on formal methods, or using formal methods as a way to prevent defects from coming into the application or work product. Formal methods provide a way to eliminate certain error sources and to verify the absence of related faults. Formal methods are of 2 types, formal specification and formal verification. Let's look at each one of them. Formal specification is concerned with producing an unambiguous set of product specification. A very interesting combination of words here. unambiguous set of of product specification, so that customer requirements as well as environmental constraints and design intentions are correctly reflected, thus reducing the chance of accidental fault injections. What this means is that when we state our specifications, when we document our specifications, there is no way that they can be interpreted in more than one ways. And we have talked about the usage of natural languages which invite ambiguity. So what formal methods do is they formally state the requirements in languages specifically designed for communication of specification. These are mathematical languages which can be interpreted in only one way. If this is done, then we can eliminate all those accidental fault injections that come into play when multiple interpretations are possible. Remember our discussion about errors of clarity and ambiguity. These things are eliminated, these errors are eliminated by using formal specifications. And formal verifications check the conformance of software design or code against these formal specifications. So once you have the formal specifications, then you have a development activity followed by a formal verification. The formal specifications say that this is what should be done, then that product is developed, followed by a verification that yes, we have met those formal specifications. This formal verification ensures that software is fault-free with respect to its formal specifications. So in other words, the formal methods have two roles to play. Number one, they have a role to play in defect prevention. And number two, they have a role to play in ensuring that actually defects have been prevented. And so that's why the formal methods are a very useful tool for defect prevention. There are a number of formal methods approaches. The oldest and the most influential formal method is the so-called axiomatic approach. The research in this area is ongoing, and depending on the real need of the software application, formal methods should be used and are being used where they are necessary. An interesting concept is that wherever formal methods are really needed, you cannot avoid using. So you have to use formal methods where they are really needed. But they are not really needed in all applications. The biggest obstacle in using formal methods is the high cost associated with difficult task of performing these human-intensive activities correctly without adequate automated support. For formal methods, there is not much automated support available. And even if that was available, the rigor that is required with the usage of formal methods is not needed in most applications of software products and services. However, in some areas where the safety of the missions is of paramount importance, application of formal method approaches is not only required but necessary, because otherwise the loss of human life and loss to the economy can be catastrophic. And because of this, that the expense involved in application of formal methods is so high, but this approach, that is the formality in ensuring defect prevention, is also very important. So there is a semi-formal method. The community is growing its interest in these semi-formal method approaches, in which the scope and the rigor of the formal method is reduced, again depending on the application, and the results are better than having no formality at all, and it is cheaper as compared to application of formal methods with full rigor. Other defect prevention approaches include formal requirements analysis, for example, the joint application development, or popularly known as JAD, formal risk analysis early in the development life cycle. Prototyping is a very important and effective way of defect prevention. Then there are structured programming methods. Remember, we talked about the impact of structured programming methods on improving the defect repair rates. Here again is the proof that structured programming methods can have good impact on preventing defects from getting into the application software. And another very important approach is to use certified reusable design and code components in the application. These components have been developed by third parties or even by the same company, and they have been used in other applications successfully, and so the number of users of those applications grow substantially with each use. And so there is a good possibility that these reusable design and code components will not let the defects come into the new applications. So these are some of the defect prevention approaches that we have talked about, and that they are successful in achieving our goal, which is to not let the defects come into the work products. Now you are looking at software defect prevention in a glance. We have on one side requirements defects, design defects, code defects, document defects, and performance defects. And on the other side, we have some approaches that are listed, and we'll see which one of them is appropriate for which application, for which kinds of defects. So we have JAD, we have prototypes, we have structured methods, case tools, blueprints, and reusable code, and quality function deployment. And as you can see, that JAD works very good for requirements defects, and it works good for design defects, but it is not very good for prevention of performance defects or document defects. Also, you have prototypes which work magnificently for requirements defects and design defects. So if we use prototyping techniques, then they work wonderfully for prevention of requirements defects as well as design defects, and they also work wonderfully for prevention of performance defects. Structured methods are very good for coding defects. Case tools are okay for design defects, but they are not very good for other sorts of defects. Then you can see that the reusable code is, or reusable documents, blueprints are very good or excellent for prevention of requirements defects, for design defects, for coding defects, and for document defects. And quality function deployment technique is excellent for design defects. So with this chart, you have noticed that defects can be prevented with different applications, with different techniques that the software engineering community has developed over the last 4 or so decades. And there are certain kinds of defects which work better with certain kinds of techniques. And so with this chart you have noticed that some techniques work better with some kinds of defects, that is the prevention of those defects, and some other techniques work better with other kinds of defects. And so the goal then becomes, and the objective then becomes, is to apply as many techniques in prevention so that the defects don't really come into the application. One thing that we have noticed is that reusable code is a good way to prevent software defects. And reusable code is good for requirements defects, that is good for design defects, it's good for coding defects and documentation defects also. But there is a limit to what can be reused. But this chart enables us to think in another way, that if we can reuse as much as we can, then we can prevent many defects from coming into our work products. And as a result, we can look at software reusability from quality assurance perspective. And so we know from the literature that reusability improves productivity, but with this information that I've just shown you, we can say that reusability also helps us in improving the quality of software. It is also to be noted that requirements defects can be prevented by different techniques like JAD and prototyping. But if you remember the chart, we had a similar chart on defect removal. We didn't have excellent results for any requirements for the removal of requirements defects. And so another way of looking at this chart is from the perspective of different kinds of defects. So requirements defects and design defects can be prevented and have a better chance in defect elimination strategy, that prevention techniques should be used as compared to defect removal techniques. As you have figured out by now that defect prevention is a difficult subject. It's a difficult thing to understand and to comprehend, that we don't let the defects come into the work products in the first place, and then to quantify them. This is the point that I'd made earlier in the lecture when I started to introduce the concept of defect prevention. But if you compare it with defect removal, there are many areas in which defect prevention works much better. And one such area is requirements defects. You have to compare the two charts that we have seen here in this lecture and we had seen in the previous lecture. So we need to learn defect prevention techniques, and we need to apply them to our software projects so that we can have a better defect elimination strategies. And there's another thing, and that is that if enough education as training is provided to software professionals, once they learn to prevent defects from software products, they will learn it for eternity. They don't have to repeat their errors. And that is the actual beauty in this concept, that you don't let the defects come into the work product, that once you have learned to avoid making mistakes, you will always avoid making mistakes, instead of making a mistake and then making a correction. So to summarize, today we started the lecture with some important concepts related to software defects. We talked about defect repair rates, we talked about defect seeding, we talked about defect tracking, and then we talked about in quite a bit of detail on defect prevention, the need, the philosophy, and different techniques that are used for defect prevention. In the next lecture, we'll talk about another interesting topic related to software quality assurance. Till then, Allah Hafiz.